Okay, here are the Chapter 11 notes. This is page 3. We have talked about solving by graphing and solving by substitution. Now we're going to talk about another method, and that's the elimination method. And what we're going to try to do with the elimination method is to create two equations that we can add together and eliminate one of the variables. If you take a look at example 3, there is not a variable that's easy to solve for. We're going to end up with fractions, which even though they're beautiful and glorious, I don't necessarily want to plug them into another equation. I am going to start by looking at the y term. I've got negative 4y and positive 3y. I can add these two equations and get rid of the y's if those two terms are the opposite of each other. So I'm going to multiply my top equation by 3. And I'm going to move it over here. That gives me a 9x minus 12y equals 3. And then I'm going to go ahead and multiply my bottom equation by 4. Notice I am not wrapping the equal sign inside the parentheses. That would be mathematically incorrect. When I multiply by 4, I get 8x plus 12y equals, what's 12 times 4? 48. Now, here's the thing, because we have done this a lot. You see an equation that looks like this, x minus 7 equals 10. I know I'm allowed to add 7 to both sides. We do that so that we can solve for a variable. I'm going to do the same thing here. It's just that my both sides are going to look different. So my 8x plus 12y, that equals 48. So I am still adding the same thing to both sides, even if they look different. 9x plus 8x gives me a 17x. I got negative 12y plus 12y. There's my 0. Equals 51. Divide both sides by 17, and x equals 3. I have an x value, but I had equations that had both x and y. So what I'm going to do right now is I'm going to plug the 3 back in for x, and I'm going to see if I can color code this. So I plug my 3 in for x, I get 9 minus 4y equals 1. I'm going to go ahead and subtract 1 and add the 4y. And I get y equals 2. So my solution should be the ordered pair 3, 2, when x is 3, y is 2. Now be careful. Sometimes we don't always solve for x first. Make sure you understand which is your x, which is your y. To be safe, I am going to go ahead and plug it into the second equation because this should work in both. So I have 2 times 3 plus 3 times 2. I get 6 plus 6, which does equal 12, so that checks. Okay. So let's take a look at how these may come up differently. Okay. And what it means in terms of our solutions. So back when we were solving by graphing, we had 3 different things that could happen. We had, and let's slide back up here, we had the consistent system with independent equations, case 1 solution. We had inconsistent system, the parallel lines, we had no solutions. And then we had the dependent systems, where the 2 lines occupied the same space, and we had infinitely many solutions. So let's see what happens when I try to cancel one of the variables. So I've got a positive 3x, I've got a negative 6x. I'm going to go ahead and multiply my top equation by 2. And I'm going to get 6x minus 4y equals 4. I'm going to leave my second equation the way it is. Negative 6x plus 4y, darn it, equals 8 up there, sorry. Sometimes you just have to look at it to know you did something wrong. Negative 6x plus 4y equals 7. When I go to add, I get 6x minus x, that's 0. Negative 4y plus 4y, that's 0. 8 plus 7 is 15. Problem is, 0 does not equal 15. This system is not true ever. There is absolutely nothing I can plug in for x and y that is going to make 0 equal 15. If you end up with a false statement like this at the end, we have no solutions. We will take a look at example 5, which starts on this page and ends on the next, in the next video.